All right, hey class. I said that I was going to make a video about some of the select problems that people had with the review. So I'm going to go through a couple of problems. We'll see how long I have, and then upload this to YouTube today so that you can look at it, and there'll be links to each problem, so you can just zip to that one if you don't want to watch the whole thing. Okay, so without further ado, we'll press for time, so let's just dive in. So the first problem is was asked about factoring the polynomial. So question 1. So let me just write down the polynomial. So from the semester A refresher, this was p of x equals to x to the 4th minus 13x squared plus 36. And the question is saying, how many times does this polynomial cross the x-axis? What's the end behavior, and what are the x and y intercepts? So to answer at least the number of crossings question and the x-intercepts question, we need to factor the polynomial. So let's factor it. This factors like a quadratic does, because this is the middle term squared. So if you were to square x squared, you get x to the 4th. X squared squared is equal to x to the 4th. So you can factor this just like you would a quadratic. So this factors like x squared and then x squared. And then two numbers that multiply to 36 and add to negative 13 are negative 4 and negative 9. Okay? So if you were to FOIL this, you'd get what we started with. X squared and x squared is x to the 4th. You have negative 4x squared minus 9x squared is negative 13x squared, and then 36. Each of these are perfect squares. Differences are perfect squares, so we can factor those further. X squared minus 4 is x minus 2, x plus 2. And then x squared minus 9 is x minus 3, x plus 3. And so you can see from this there's 4 distinct numbers that would make this polynomial 0. 2, negative 2, 3, negative 3. And so it's going to cross the x-axis 4 times. So there's 4 crossings. 4 crossings. Okay. And so we've already found the x-intercepts. So the x-intercepts are x-ints are at 2, negative 2. I'm just going to list out the numbers that they are. They all have y-coordinate 0. So 2, negative 2, 3, negative 3. That's all of them. And the y-intercept is found by plugging in 0 to the polynomial. Remember, a y-intercept is where it hits the y-axis, so that's when x is equal to 0. An x-intercept is when y is equal to 0. You can have many x-intercepts for a function, like this one has 4. You can only have one y-intercept for a function because if there were more than one, it would fail the vertical line test. Okay? So our y-intercept is if you evaluate p of 0, and p of 0 is just 36. So the y-intercept is 36. And then, let me scroll down a little bit. Okay. And then what else? Then the last, I skipped question part B because we kind of already had gotten to the x and y intercepts. So the next question is, part B is saying what's the end behavior? End behavior of the polynomial is looking at the highest term. So p of x is equal to x to the 4th plus stuff. And when I'm looking at plugging in big numbers, which is end behavior, the stuff doesn't matter, because x to the 4th is way bigger than anything else. And so I just look at that leading term and I see, is it a positive or negative leading coefficient? So is there a positive or negative number multiplying this? And then that's going to flip your polynomial, right, across the x-axis. And then I look at the degree and I say, is this even or odd? You know, because an even polynomial, both arms will be going up or down. And of course the up or down is if there's a negative or positive in front. And then if it's an odd degree polynomial, then the arms are going to be going in opposite directions from each other. So this is even, and there's no negative in front. And so an even degree polynomial is going to be either like this or like this. And since it's a positive leading coefficient, it's this one. So that means as x goes to either plus or minus infinity, so in either direction, the polynomial p of x is going to go to positive infinity. So it will get increasingly more positive if you plug in a big negative or a big positive number. Okay, so that's question 1. Okay, question 2 is a little bit more involved. For question 2, it's all about graphing a rational function. So remember, when you're sketching a rational function, that you need to find any x-intercepts, y-intercepts like usual. But then rational functions have vertical and horizontal asymptotes, so you need to check for those. And then if there's common factors, you might have a hole in the function, and then lastly, you just start sketching. And if you need to kind of like figure out which side of my vertical asymptote I am, you can do sign analysis to figure that out. So here's our rational function. It's 2 minus x over x squared minus 1. So what I'm going to do first is I'm going to factor the numerator and denominator completely. So this can be rewritten as 2 minus x, not factorable, x minus 1, x plus 1. Or rather, there's no reason to factor the numerator because, I could factor a negative sign out if I wanted to, but it's not necessary. Okay, so that's it, factored. There's no common factors, so I can't simplify it. So there's no simplifying to do. We just look at what makes the denominator 0, and those are going to be vertical asymptotes. And then we look at what makes the numerator 0, and those are going to be x-intercepts. So vertical asymptotes are when you're doing a number divided by 0, and x-ints are when you're doing a 0 divided by a number. Okay? Because 0 divided by a number is 0, so it's going to be equal to 0 there. And if you're doing a number divided by 0, that's undefined. So that's going to be that blowing up asymptotic behavior. So vertical asymptotes, we have x equals 1 and negative 1. Those are our vertical asymptotes. I'll put a little at symbol. So those are going to be two vertical lines that this function cannot cross. A horizontal asymptote, we'll get to that one. Let's talk about horizontal asymptote. So a horizontal asymptote we need to find, and that's where you're looking at the numerator divided by the denominator, just the degrees of those polynomials. If they've got the same degree, then they kind of tie. The two functions grow at the same rate. So if the degrees are the same, so for a horizontal asymptote, compare degrees of n and d. So the numerator and the denominator. If they have the same degree, they grow at the same rate, and so you just take that ratio of leading coefficients, whatever the two numbers are. If the numerator's got a greater degree than the denominator, you simplify it, and then you look at that polynomial. It's got polynomial behavior. And then the last case, which is this one, is if the numerator's degree is smaller than the denominator is growing faster, and so this function is going to head to 0 because you're doing something divided by something bigger. So, even if that number on top is 1,000, that number on bottom is 1,000,000. 1,000 divided by 1,000,000 is really small. If you divide these numbers, 1,000 divided by 1,000,000, you end up canceling all these zeros, right? And you get 1 over 1,000, which is a small number. And so that number is heading towards 0 as the x's get bigger. So that's the case we've got here. I'm just looking at this ratio. So what does the function look like? It looks like negative x over x squared. Those are the two leading terms. And if I were to simplify this, then this is negative 1 over x. So I just threw away everything else, which were just those constants. And I would throw away factors of x as well. So I'm only looking at, let me get a color here. I'm only interested in this guy, the biggest term in the numerator, and this guy, the biggest term in the denominator. So I divide those. Okay, simplify. You get negative 1 over x. And what happens as x gets bigger and bigger is that this is going to go to 0 because negative 1 divided by something huge is still very close to 0. So if that number is any constant on top and the denominator is any factor of x, then you're going to go to 0. So that's our horizontal asymptote, is at y equals 0. Okay, so we've got that horizontal asymptote, those two vertical asymptotes. Let's do our x and y intercepts. X-ints, we just have at x equals 2, so that's an easy one. That's the numerator equal to 0. And then, let's see if I can scroll down. Okay, running out of space. And then what else do we need? We need a y-intercept. So our y-intercept is if we were to evaluate at 0, so the y-int, y-int is the function at 0, which would be r of 0, and that's 2 over negative 1, so that's negative 2. Okay, so with all these things in hand, what we're going to do is plot as much of this information as we can, and then what we don't know, we can either do some sign analysis to figure out which side of an asymptote we're on, or some logic to figure out which way the curves are going to be going, or we can just plug more points in if we have to. That's the brute force method, is to just get your calculator out and plug in different points and plot those. Okay, so let's go ahead and start sketching this. So we've got two vertical asymptotes. Here's 1, negative 1. So I'll sketch those in 1 and negative 1. I'll use a different color for the graph. And our horizontal asymptote's at 0, so I'm not actually going to draw that one. Our x-intercept is at 2, so at x equals 2, we've got, oops, go away. I'm going to draw blue. Okay. This isn't letting me draw for some weird reason. Draw. So there's our x-int. We have a y-intercept at negative 2. So down there. And now we have to use some kind of, logical reasoning to figure out what this function is going to do. We know that it approaches the asymptotes when the function gets close. So it's going to kind of squeeze close to those asymptotes. So the first one I'm going to look at is this middle section of graph around that y-intercept. Now we know that it can't cross in the middle. So here, I'll kind of highlight. Maybe I can use there's not a highlighter. Okay, so it can't cross here. And the reason why it can't cross here is because it would have another x-intercept. And we know there's only one x-intercept at 2. So that means that the function has to curve down and to the left here and down to the right there. So let's go ahead and get that behavior. So it's going to curve down this way and down that way. And then we analyze what's happening on either side of these asymptotes, and we can plug numbers in if we need to. So if I think about what's happening just on the right side of 1, so like a number like 1.1, so r of 1.1 is equal to 2 minus 1.1 over 1.1 minus, oops, should be I don't know. Eraser. 1.1 minus 1, and then 1.1 plus 1. And I mean, I could actually get a number for this, but I'm not interested so much in the answer as I am interested in the sign. Is this a positive or negative number? If it's positive, we know that it's going to be up here, and if it's negative, we know it's going to be down there. The numerator is positive, so you get positive on top because 2 minus 1.1 is a positive number. We've got a denominator that's a positive times another positive number because 1.1 minus 1 is positive and 1.1 plus 1 is positive. So the overall result is positive. So that means that it's not down here, but in fact is up above the x-axis. So just at 1.1 we are positive. And so then how's this going to work? Well, it's got to pass through that point, so we know we're going to go through, and then it's got to rebound and kind of spring back towards that horizontal asymptote at 0. So remember, there's a horizontal asymptote at y equals 0, so it will approach that from below the x-axis. And I can just double check that it's approaching from below, because if I look at this function, let me scroll up, if I look at this function and I plug in a big positive number, like 100, we're going to have a negative on top and a positive on bottom. And so we've got negative 98 divided by, you know, a positive number on bottom. So we get a negative but very small number, okay? So you could plug in 100 if you wanted to. I won't go through that, but yeah, so if you evaluate it at 100, you get a negative but small number. So that's why it's below the x-axis. Then lastly, what happens on the other side, which is this section over here, what's going on? Well, we could do sign analysis again. We know we're either going to be up here or down here based off the fact that it can't cross the x-axis again. We only have one x-intercept. So we have to look and say, are we above or are we below? And so it's not, you can easily, you can do a sign analysis, or you just plug in a number and see if it's positive or negative over here, because if it's positive, it's above, if it's negative, it's below. So we could try that. If I plug in -2, for example, I get a positive numerator and I get a positive denominator, right? -2 minus -2, that's going to be 4. -2 squared, that's going to be 4 minus 1 is 3, so we get positive, and so that means that we are up here. And whoops, we're up on top, not on bottom. So we'll go ahead and get rid of that bottom part. And sketch in the function up here. And that's about as good as you need it. You've got your x-intercepts, you've got your y-intercept, you've got your vertical asymptotes, your horizontal asymptote, and you've got the right places for where the functions are. Okay, so that's question number 2. It's a long one, but and just so you're aware, the exam isn't going to have you actually do graphing rational functions, but you will have to find x-intercepts or y-intercepts or match a graph or that kind of thing, because those are the questions I could ask you for multiple choice. Okay, so the next question was about finding the inverse to the function f of x equals x over 1 minus x. Now, it's a little bit tricky, and the domain and range of the inverse. Now, it's a little bit tricky to find the domain and range of the original. Well, the domain is actually pretty easy to find, but the range is trickier. So what we'll do is find the domain of this function. So its domain is just everything except 1. So x cannot be 1. Another way to say this is it's -infinity to 1, union 1 to infinity. So that's all the numbers that are not 1. Everything else is good to go. So that's the domain. What's less obvious is what is the range of this function. So I'm going to hold off on finding its range. Because when we do the inverse algebraically, we'll be able to find that function's domain pretty easily because it's a rational function. And then the domain of that inverse function is going to be the range of the original and vice versa. Okay? So let's go ahead and find the inverse algebraically. Now to do that, we set this function equal to y. So we say y equals x over 1 minus x. And then I have to do some algebra to get x by itself. Well, x is in two places right now, so what I'll do is first multiply both sides by 1 minus x. And my goal is to try to get x out of the denominator, so we did that. We have x, and this is y minus xy after I distribute the y. And now we'll collect all the terms with x to one side, so we'll get x by itself, or get all the x's to one side, so we can add xy to both sides. And that means I have y equals x plus xy. And then lastly, we'll factor out x from the right-hand side, and that will kind of isolate x. So this is x times the quantity 1 plus y equal to y. Divide both sides by 1 plus y. And there we go. We have x equals y over 1 plus y. And often when we write this with inverse function inverse notation, we'd say f inverse of x equals x over 1 plus x. So that's the algebraic inverse. This is the undoing function for the original one. And I can identify the domain of this function pretty easily. Let me zoom out a little. So the domain of this function is, domain is x cannot be negative 1. Or another way to say this is negative infinity to negative 1 union negative 1 to infinity. And so since this domain is pretty easy to find because I just look at the denominator and say, hey, I can't plug negative 1 in. But the range is less obvious, except I did that work earlier to find the domain of the original function. And we know that when we do inverse functions, if they're one-to-one, the original function's domain is the inverse function's range. And the original function's range is the inverse function's domain. So they swap because what you're doing is taking all the y's and putting them back to the x's and so forth. So I know the domain of this function. It's everything except for 1. So this is y cannot equal 1 because the domain of the original function was that same set. It is everything except for 1. So we now know the domain and range for both functions. 1 to infinity. The original function is going to have a domain of everything but 1 and a range of everything but negative 1. And then the inverse function is the opposite of those. A domain of everything but negative 1 and a range of everything but 1. Okay, so that's finding the inverse for this rational function. Okay. All right, moving on to Unit 4 review. So question 3 was asked about first, and question 3 is asking what are the lengths of each circular arc connecting the points 0, 1, and negative root 2 over 2, negative root 2 over 2. So I'm going to plot these on the unit circle. We have 0, 1 is at the top of the unit circle. Here's my circle. And negative root 2 over 2 is in quadrant 3. So this question is asking about the lengths of the arc right here and the length of the arc right here. What's the length of each one of these? So if I find the angles in radians, I will know these two lengths of arc lengths because the angle in radians, or the difference in the angle, if I know this angle, or either angle for that matter, I know this angle right here, then that angle in radians is the length of the arc. So I'll just write that down. The angle in radians is the arc length on the unit circle. Something like that. Okay, so just knowing the angle in radians is enough. So we know this angle up here is pi over 2. And we know this angle down here is 5 pi divided by 4. Remember, if you kind of cut this up and cut the top into quarters, you can count the quarters of pi. We have 1, 2, 3, 4, 5 quarters of pi. And then we have 2 quarters of pi for the point at 0, 1. And so if I subtract these, 5 pi over 4 minus pi over 2, that's going to get me 3 pi over 4 as this red arc. Okay? And this is true on the unit circle, arc length. So theta rad times the radius is equal to arc length. And if it's not on the unit circle, you just scale it by r, right? So all it is multiplied by the radius to get the arc length. So that's why angles and radians are so nice, is because they really easily map to length around the unit circle, or around a circle of any size. You just take that angle in radians, multiply it by the radius to get the arc length. And if r is 1, like the unit circle, then it's just the angle in radians. Okay, so then the blue arc is 2 pi, which is the whole circle circumference, minus the red arc, which is 3 pi over 4. And if I subtract these, I get 8 minus 3, so that's 5 pi over 4. So those are my 2 arc lengths. Okay, so someone asked about question 4, which is just converting to radians. Oddly, they didn't ask for question 6, which is converting to degrees. So I'll just give you the formula that converts back and forth between the two. So you have this equality, 180 degrees equals pi radians. Okay, so that is the conversion factor. You're either multiplying by 180 over pi or multiplying by pi over 180. So it's either multiply by 180 over pi or multiply by pi radians over 180 degrees. So whatever units you have, you look for the one that has those units in the denominator, and then those units will cancel and you'll end up with either radians or degrees. So if I've got 30 degrees and I need to multiply this by something to get radians, then I need my degrees to be in the denominator. So I'm going to multiply this by pi radians over 180 degrees. And if I do this, I'm going to get pi divided by 6. Okay, because you can divide the top and bottom by 30, and that 180 divided by 30 is 6. So you can do this for the other problems. Going from radians to degrees, you just multiply by this factor. Other way around. If you're going from radians to degrees, you'd multiply it by this factor, and if you're going from degrees to radians, so this is r to d, then you multiply it by this factor. Okay? Easy enough. Okay, question 10 is asking for evaluating cosine and sine given knowing what tangent of that angle is and what quadrant the angle is in. So you know if the angle is in between 0 and pi over 2 and tan of the angle is 2, we're living in quadrant 1 because we're greater than 0 and smaller than pi over 2, which is 90 degrees. And this is telling us that the slope of the radius is 2. Okay? Just reminding you that tangent is equal to slope. So if we were to kind of give an eyeball of that here's my unit circle, then I need my slope to be about 2. So it looks like we're somewhere up here. So my intuition should be that the sine is greater than the cosine. The sine of theta is bigger than the cosine of theta, since our slope is steep. So this is theta. Okay, so if I want to figure this out, you can look at this triangle here. Here's 1, here's theta, and I know the slope is equal to 2, so this is 2x over x, okay? So another way of thinking about this is tan of theta is equal to sine of theta over cosine of theta, and that's equal to 2, and so sine of theta is equal to 2 cosine theta. So either way you want to think about this will work. So if I look at the triangle, I can just use triangle trigonometry to find out what x is. That's going to be cosine, and then double that to get sine. Or if I look at this expression for sine and cosine, I can use the Pythagorean identity, which is the same thing, to solve this for sine or cosine. So let's do the triangle first, and we get x squared plus quantity 2x squared equals to 1 squared. And so this is x squared plus 4x squared equals 1. So I get 5x squared equals 1. So x is equal to the square root of 1/5, which is root 5 over 5. Now I didn't put the plus or minus there because we're in quadrant 1, and I know that the x is positive because we're in quadrant 1. Okay? So I just neglected the plus or minus. For yourself, until you really understand the quadrants, I would put plus or minus and then remember to choose based off of the quadrant. Okay? So quadrant 1, so this fact says that cosine and sine are both positive. So this is cosine of theta. And then sine of theta is just twice that, so that's easy, equals 2 root 5 over 5. So I've got my sine and my cosine. If I don't use this triangle method and I just use the Pythagorean identity, that's fine too. So here's the Pythagorean identity. So from here, we know that sine squared theta plus cosine squared theta is equal to 1. And if I make the substitution, I get 2 cosine theta quantity squared. So I'm replacing sine with 2 cosine theta plus cosine squared theta equals 1. So I get 4 cosine squared theta plus cosine squared theta equals 1. Hopefully you see where this is leading. We get the same equation. We get 5 cosine squared theta. We just write it as cosine theta instead of as x from the triangle we have over there. So this is going to solve exactly the same as this will. Okay? Alright, so that's how you find cosine and sine when you know tangent. Alright, so the next question, 14, is kind of related to the one we just looked at. 14 says, given the angle is in between 0 and pi over 2, so same interval, we're in quadrant 1 again, and tan of theta is equal to 2. Come up with expressions for cotangent of theta, secant of theta, and cosecant of theta. So cotangent of theta is the easiest one. That's 1 over tan of theta. And so that's equal to 1 divided by 2. So that's no need to simplify that further. And so trickier might be finding secant and finding cosecant. Well, if you're going to find secant, you've got to find cosine, because this is equal to 1 over cosine of theta. And so we already went through how you find cosine in the last example. And cosecant is 1 over sine of theta. And we already went over how to find sine of theta from the last example. So 1 over cosine theta is equal to 1 over root 5 over 5. And so that would be equal to 5 divided by root 5, which you could simplify, multiply the top and bottom by root 5, and you get 5 root 5 over 5, which is square root of 5. So that's the secant of theta. That should be at times. Hold on, let me fix that. Okay. And then you can do the same thing with sine of theta. So this is equal to 1 divided by 2 root 5 over 5. And so that's equal to 5 over 2 root 5. And multiply the top and bottom by root square root 5. And that gets you, again, root 5 over 2 after simplifying it. So solving this problem just amounts to knowing how to find cosine and sine. And then you just take the reciprocal to get those. Okay, next problem, number 20, is asking about a lighthouse on an 80-foot tall hill. So we have an 80-foot tall hill and then a lighthouse on top of that. This is my great lighthouse. So this is 80 feet. 80. And you calculate the angle from the ground to the top of the lighthouse to be 58 degrees. So you're measuring this angle as 58 degrees. And you calculate the angle from the ground to the top of the hill to be 42. So this angle here is 42 degrees. Oops, degrees. Okay. So the question is, how tall is the lighthouse? So what we've got to do is set up some trig expressions here. We've got two right triangles to worry about. We have one that's this 80 foot, 42 degree right triangle, and then we have one that is a bigger one, which is 80 plus x. And our question is, what is x? And this is 58 degrees. And because we haven't moved ourselves at all, we know that the bottom side of both of these right triangles are congruent, that they're the same length. So we can figure out the bottom side from this triangle, and then when we know that side, we can put it into this one to find the long side of the other right triangle and subtract off 80 to get x. Okay? So let's call this one y. I know we've got our x's and y's flipped around, but whatever. So we know that tan of 42 is equal to 80 over y. So y is equal to 80 divided by tangent of 42 degrees. Let's divide by y, divide by tangent of 42, and that gets you this expression. And we can calculate this. Whatever that is. Let me get my calculator. 80 divided by tan of 42. We get about 88.8 feet. And then we'll plug that into the other triangle and use that to find what x plus 80 is. So we now know tangent of 58 degrees is equal to x plus 80 over 88.8. I'm going to use that whole number in my calculator to figure this out. So I get 88.8 times tangent of 58. And I get x plus 80 is equal to 142.19. And that should be 80. And we subtract 80 and we get x is equal to minus 80. X is equal to 62.19. So the lighthouse is about 62.19 feet tall. Okay, the next question is about solving a trigonometric equation. And we've got, our equation is cosine squared x plus 3 cosine x plus 2 is equal to 0. So this should scream out to you that this is a quadratic equation because we have something squared plus a number times something plus something equals 0. So we're going to solve this by factoring it, and then you can substitute if you want, or you can just factor straight away. If it doesn't factor, then you would use the quadratic formula. So let's just do this with substitution and make it look nicer. We have y equals cosine of x, because that's the expression that's in the quadratic form. So that gives us y squared equals cosine squared x. And so if we make this substitution for each of these guys, this gives us y squared plus 3y plus 2 equals 0. So first try factoring. If it doesn't factor, quadratic formula. This one factors nicely as y plus 2 and y plus 1 equals 0. And then at this stage, we can make our substitution of cosine back in. So we do that substitution, and that gets us cosine, cosine x plus 2 and cosine x plus 1 equals 0. Let me remind myself that we're looking for the answers between 0 and 2 pi. So we want those numbers. For this one is not possible because cosine is never never less than -1. This is saying cosine of x plus 2 equals 0, and that can't happen because this would say cosine of x equals -2, and we know that never works because the smallest cosine of x can be is -1. However, this other one does work. Cosine of x plus 1 can equal 0. Cosine of x is -1, and so that says x is equal to, if I think about the unit circle, where is cosine equal to -1? My x is -1 over here, so that's at pi. So that says x is equal to pi plus any multiple of 2 pi thereafter. It's 2 pi n. So I can go around the unit circle as many times as I want, and I will still get the same answer. And so I want the ones between 0 and 2 pi. This is pi, 3 pi, 5 pi, and -pi, and so forth. So it's odd multiples of pi. So the only one that's in the interval is that one. So pi would be the answer to this. You can always check it with a calculator by plugging pi back in, pi in here, and you should get 0 as a result. Okay, so our next problem is to evaluate is number 25, which is to evaluate sine inverse of cosine of 4 pi over 5. So remember that sine inverse, the answer is going to be an angle. This is an angle. Since sine inverse takes a x or y value from the unit circle and returns back an angle, and the answer is going to be between -pi over 2 and pi over 2. So somewhere in the right half of the unit circle. So it's going to be an angle between -pi over 2 and pi over 2. Okay? So that's just to remind ourselves what we're looking for. And if our answer does not fit that, then we made a mistake. And I know all of this because we're looking at the answer. The last thing we're doing is doing inverse sine of something, which means that we're getting an angle, and our angle is going to be between -pi over 2 and pi over 2. So we're going to sketch this. Let's say cosine of 4 pi over 5 is equal to some value t. So we sketch a 4 pi over 5 angle, and then we know where t is. So 4/5 of pi, that's, if I were to kind of go, this would be 5/5, so I could cut up the top into fifths, and we would get something like over here. Okay, I just basically need to know the quadrant. So there's my 4 pi over 5 angle, 4 pi over 5 angle, and so that tells me that this is t. So the x coordinate is t. It's t whatever. I don't care what that thing is. And now we want to find sine inverse of t. and that's going to equal some angle. It's equal to the angle theta, where sine of theta is equal to t. And so where is that? So t is a negative number, and that means that our y-coordinate has to be down here. So here's a y-coordinate of t. And the angle is between negative pi over 2 and pi over 2, and so that means that our angle is in quadrant 4. So here's my triangle. Let me get rid of this. Okay, so that's my triangle that is got this angle of theta. So we know theta is going to be an angle, negative number because of this. So we can kind of look at this triangle here, and we're interested in theta. We know that this side length is t, and that's 1, and so the angle here is the same angle, is congruent to this angle because they're the same triangle. They're just turned. And this angle is pi over 5, since it is what's left if you were to get all the way to pi. So this angle here is pi over 5. And so what would theta be? Theta is going to be pi over 2 minus pi over 5. But then, since it's in quadrant 4, let me get a little extra space. Since it's in quadrant 4, we know it's the negative of that. Theta is equal to the negative of whatever this is. Okay, because it's in quadrant 4, and this is a positive angle right here, and we need to be in quadrant 4, so it's going to be negative. So what this is, if I were to kind of simplify this, we have, or to get a common denominator, I need to get tenths, 5 pi over 10 minus 2 pi over 10, and negative of that. And ultimately, that's going to get me negative 3 pi over 10. So that's what theta is. And I can verify this with a calculator. If I were to do the sine inverse of cosine of 4 pi over 5, sine inverse, make sure I'm in radian mode, sine inverse of cosine of 4 pi over 5, I don't know if you can see this, but you get negative 0.9424, and then I'm going to do negative 3 pi over 10, and calculate that one as well, and you get the same answer. Okay? So that's nice. That's how you check. Okay, next we're going to look at 27, which is, you've got t is a number where cos inverse of t equals 1, and you want to find cos inverse of negative t. And you also want to find sine inverse of t. Now, I could go through the process of drawing these again, and I will, but there's also two formulas that are nice to recall. One is that cosine inverse t plus cosine inverse negative t is equal to 0. And then the other one is that cosine inverse of t plus sine inverse of t, oops, I don't need parentheses. Cosine inverse of t plus sine inverse of t add up to pi over 2. So the first one is saying that cosine inverse of t and cosine inverse of negative t are going to be angles that are negatives of each other. And then the second one is saying that cosine inverse of t and sine inverse of t are complementary angles, so they add up to pi over 2. So the first one, you can kind of give a rough argument why that's the case. If I were to look at, oh wait, no, this is incorrect. So it's not that they add up to 0, it's that they add up to pi. This is pi. So why is that? Well, if we sketch an angle for t, for the first one, So say my t is some positive number here. Then that would be the cosine inverse of t, theta. Let me zoom in a little bit. So here's my t. And then we have another, this is negative t. So this would be, let's actually erase this. So this angle here is cosine inverse of t, and then the bigger angle is cosine inverse of negative t. And so if you were to check, these are congruent angles, and so if I were to stack the angles on top of each other, let me use some colors. We have cosine inverse of negative t, and then this extra bit is cosine inverse of t, since these are congruent. And so if I were to add red to blue, we're going to get pi. So these angles add up to pi. And then the sine inverse of t and the sine inverse of negative t add up to 0. They're negatives of each other. Okay, let me zoom back out. Okay. So with that formula in hand, it's not too hard to find the answer to this. We have cosine inverse of t plus cosine inverse of negative t equals pi, and we know this one is equal to 1 plus cosine inverse of negative t equals pi. And so cosine inverse of negative t is equal to pi minus 1. And then for sine inverse of t, we use the fact that they're complementary angles. So the fact that they're complementary would say that sine inverse of t is equal to pi over 2 minus cosine inverse of t, which is equal to pi over 2 minus 1. Okay, so having those formulas is helpful, and just remembering why that's the case is useful as well. There's the third formula is this one: sine inverse of t plus sine inverse of negative t equals 0. So those are negatives of each other. Okay. Okay, I'm going to skip 28 because you can use those same formulas that I showed in the last question to solve that problem as well. So we'll move on to the sinusoidal modeling questions, which are getting a graph, writing an equation, and solving for specific times. So this one is saying we have a water wheel with the diameter of 30 feet, so 30 feet in diameter, and it says a fish gets picked up at the water wheel and goes for a ride. So it doesn't really matter if we're going clockwise or counterclockwise for the height. So the fish gets picked up here at t equals 0. There's my fishy, whatever, fish. And if we're going this way, its height will increase. It says at t equals 75 seconds. Oh, sorry, the water is right here at 10 feet. So this is a depth of 10 feet. Can I spell? I don't even know what I'm saying. It's a depth of 10 feet. So we have a 30-foot wheel and we have a depth of 10 feet. So the fish goes up, and at 75 seconds, t equals 75, it's up at the top of the wheel. 0 seconds, it's picked up at the bottom, and 75 seconds, it's at the top. Okay, so we can approach writing the equation two ways. We can either use the values that are given to figure out the equation, or we can sketch the graph and use the graph as a guide for writing it. So let's go ahead and sketch the graph. We know we can call the kind of point of water, the top of the water, as h equals 0. And so that means that initially the height of the fish is negative 10. So h at 0 is negative 10. Okay, so it starts 10 feet below water. And then we're given the other information that at 75 seconds, it's at the top of the wheel, which is going to be 30 feet above -10. So that would be at 20, which is 20 feet above water. And then it will go back down and back up and back down and so forth. And so what we figured out, this is half a cycle. So half a cycle is 75 seconds. Okay, so one cycle is 150 seconds. So it takes, what is that, 2.5 minutes for it to make one full revolution, 150 seconds. Okay, so let's go ahead and sketch this graph. Oops, let's get my pen. So here's my h, height equals 0. And we know initially it's at 10 seconds. So I'm actually going to mark some time intervals here. So we have 20 up here, -10 down there. This will be 75. This will be 150. This will be 150 plus 75 is 225. And then this will be 300. Okay, so that gets us some good plots to point. Points to plot. There we go. So at 0, it's at -10, so that's where the fish is initially. At 75, whoops, give me red. 75, it's at 20 feet. That's right here at the top of the wheel. Mark it red, whatever. And then, so at 75 seconds, it's at, man, can I just mark this red dot? No? Mark a red dot. What the hell? Wow. Sometimes technology doesn't work the way you expect it to. What the heck? Draw a red dot. Freaking red dot. Don't want to type. My goodness. Okay, I think we got our dots now. Maybe? Let's see if I can zoom in here or something. It doesn't want to draw my dot. That's really annoying. Alright. I apologize. This is like not working the way I wanted to with the touch screen. Okay, so anyway, it's going up. This is awful. And it reaches a peak at 75 seconds. 150 seconds is back at the bottom. So we're at -10 here. We're at 225, we're back at the top. At 300, we're at the bottom again. So our function is going to look something like this. Here's our graph. Okay, so that's the fishy's journey. The next part to this question is to come up with an equation. So the equation of our fish is we would find the mid value. So if we take the average of 20 and -10, 20 plus -10, and divide it by 2, our mid value is going to be 10 over 2, which is equal to 5. So the midline is at h equals 5. And we can see that if we start at 5, we go up 15, we're going to go up to 20. And if we go from 5 down to -10, we're going to go down 15. So our amplitude, so this is the sinusoidal axis. This is the midline, SA for sinusoidal axis. And then our amplitude is going to be equal to 15, which is 20 minus the sinusoidal axis. Okay? Oops. So it's equal to 20 minus 5, which is equal to 15. The next step is to figure out what the period is. Period should be period and the period, period is equal to 150 seconds, because that's how long it takes for it to make one full cycle. And then if we need to have any phase shift, and the answer is yes, we need a phase shift for cosine. Phase shift right by 75 seconds. And reason why we need a phase shift this right 75 seconds is because cosine's graph would start at the top, and we will actually want the top of the graph to be 75 seconds later. To be 75 seconds to the right. So using all this information, we can come up with our equation for the height. So we have, let's see, in red, we have h of t is equal to the amplitude, 15, cosine of 2 pi divided by the period, 2 pi over 150, t minus the phase shift, 75, plus the sinusoidal axis, 5. And so that function right there would model this height for the fish. And then the question is, when does the fish first exit the water and when does it re-enter the water? So it's asking for 2 times. The times I'll highlight in green. So it's asking about this time and this time. So when does it first exit the water? So this is exiting, and this is re-entering the water. And so we're asking, when is when is h equal to 0? What t's would make h equal to 0? So we'll go ahead and solve this, set this equation up and solve it. I'm kind of running out of space, so we'll do it over here. Okay. So here's my h equation. So we've got 0 equals 15 cosine 2 pi over 5, 150, t minus 75 plus 5. So we get, subtracting 5 from both sides, we get negative 5 equals 15 cosine 2 pi over 150 t minus 75. So we get negative 1/3 equals cosine of 2 pi over 150 t minus 75. Okay, so solving this equation, we get, let's see here, negative 1/3, so we get cosine inverse of negative 1/3 plus or minus, because remember cosine inverse, you have the positive angle and you have the negative angle, they both get you the same value, plus 2 pi n equals 2 pi over 150 t minus 75. We're getting there. We multiply both sides by 150 divided by 2 pi, so times 150 over 2 pi times this whole thing by 150 over 2 pi, so we get plus or minus 150 over 2 pi cos inverse of negative 1/3 plus 150n equals t minus 75. And so from here, I'll just evaluate these numbers. So 150, let's make sure I'm in radian mode, 150 divided by 2 pi times the inverse cosine of negative 1/3. This is equal to 45.6, roughly, plus 150n, plus or minus. And then we add 75 to both of these. So that gives us 120. So this equals t minus 75. So if we add 75, okay, so we add 75 to both sides, whoops, plus 75, so that gives us t equals 120.6 plus 150n, or negative 45, 29.4 plus 150 N. Okay, and so those are the 2 times plus multiples of the period where the fish is entering or exiting the water. So if we go back to our graph, so we've got 29.4 plus 150 N, 120.6 plus 150 N. So these would be the first 2 times. This one and this one would be the first two positive times where it's entering or exiting the water. Let's go back to our graph up here. So it looks like our 2 answers are going to be, what was it, 29.4, 120.6. So 29.4, looks like that's this time right here, 29.4. And then the other one was 120.6, and that's this one right here. And that matches with what our graph looks like, and you can evaluate it on the calculator to check. Okay, it's a long problem, but there's a lot of parts to it, particularly solving at the end once you have your function. Okay, let's move on to the next question. Okay, question 32 says that the height of a yo-yo can be modeled with a sinusoid. Suppose the yo-yo starts at a height of 3.3 feet and is dropped to a height of 1.1 feet. The time it takes the yo-yo to make a full revolution is 2 seconds. We want to sketch the graph of the height of the yo-yo in feet versus time. So we're dropping a yo-yo. It starts off at 3.3 feet, so h of 0 equals 3.3. And then we're given that at 2 seconds, it's back at 3.3. And so halfway in between, h of 1, it's at the bottom of its drop, because it's at the top 2 seconds later. It takes a revolution, takes 1 cycle is 2 seconds long. So halfway in between, it's going to be at 1.1 feet. So those are our kind of 3 points we can use to sketch the graph. So here's 3.3, here's 1.1, and we've got times of 0, 1, 2, 3, and 4 seconds. So if I sketch this, that means we start off at 3.3, at 1 second we're at 1.1, at 2 we're back at 3.3, 1.1, 3.3, so that's our curve. Okay, so that's the graph of the function. Now we want an equation, so let's find our sinusoidal axis. So what is the sinusoidal axis? Well, that would be the average, 3.3 plus 1.1 divided by 2. That's 4.4 divided by 2, which is 2.2. So the average is 2.2. And the period is equal to, so let's do amplitude next. So amplitude is another easy one to get. Amplitude is equal to 3.3 minus 2.2. So the difference from the top to the middle, or from the middle to the bottom, and that's equal to 1.1. So that's our amplitude. That's the sinusoidal axis. The period is going to be the time it takes to repeat. That's just 2 seconds. That's given to us. And then we have the phase shift. And if we use cosine, there's no phase shift because it starts at a peak. If it did start at a peak, we'd have to move our peak to the right by some amount to get a peak to line up. So there's no phase shift, which is great. So let's go ahead and write the equation. So we have h of t is equal to 1.1 cosine of 2 pi divided by 2, it's the period, times t minus 0. So I'm just going to not write that. So times t plus the sinusoidal axis, which is 2.2. And so that would be our function. So we could write this just as pi t. So this is equal to 1.1 cosine of pi t plus 2.2. And then the third time the yo-yo is at 2 feet, so we're interested, I'm going to sketch this out. So we want to know when is it at 2 feet, and the third time, so 2 feet is like right about here, underneath the sinusoidal axis. So this would be the first time, second time, third time. So this is the one we want. X marks the spot. So from the picture, it should be between 2 and 3 seconds. So that's a good way to check our answer once we compute it. So let's go ahead and calculate this. So we need to find out what t would satisfy this equation. 2 equals 1.1 cosine of pi t plus 2.2. So we'll subtract 2.2 from both sides. We get negative 0.2 equals 1.1 cosine pi t, and divide by 1.1, and that gets us negative 0.2 divided by 1.1, negative 0.18 repeating equals cosine of pi t. So now we take the inverse cosine, we get plus or minus inverse cosine of negative 0.18 repeating plus 2 pi n equals pi t. Divide by pi, and that gets us plus or minus 1 over pi cos inverse of negative 0.18 repeating plus 2n equals t. So those are all of our equations, all of the times. Let's go ahead and evaluate this. We have inverse cosine times divided by pi. So this would be plus or, oops, running out of, plus or minus 0.56 plus 2n is equal to t. And we want the third time. So if we were to sketch these out, we'd have to start plugging in n for different values of n. We'd have 0.56 as the first time. Then we'd have the negative plus 2, which is equal to 1.44. And then the next one would be 2.56. And then we'd have 3.44. They're all separated by 2 seconds, which is really nice. 4.56, and then 5.44. And they would just keep repeating this pattern. Each one of these is 2 seconds apart. 2 seconds apart. Okay, hopefully that's a little easier to see. And so the third time is this 2.5 second one. So when t is equal to 2.5 seconds, the yo-yo is at 2 feet, and that's the third time it would be at 2 feet. So we could go back to our graph and just verify 2.56 makes sense for our picture, and yes, it does, right? Here's about 2.56. It's about 2.56. Is right there. Boom. And the other ones would be here and here and there and so forth. Okay? Alright, so done with that problem. Okay, now we're into Unit 5 review. So the next question was asked about solving problem number 3 from Unit 5, which is what is sine of pi over 12 given that cosine of pi over 12 is equal to the square root of 2 plus root 3 all over 2. So we want to find an exact expression for sine pi over 12. So we'll just use the Pythagorean theorem, Pythagorean identity, which says that cosine squared pi over 12 equals sine, plus sine squared pi over 12 is equal to 1. So when you add cosine squared and sine squared, you get 1. And we'll substitute in what we know cosine pi over 12 to be. So this is the square root of 2 plus root 3 over 2 squared plus sine squared pi over 12 is equal to 1. So simplifying the square root, or squaring this, we get the square of the numerator is 2 plus root 3. That removes the square root, the external one. And squaring 2 gets us 4. Plus sine squared pi over 12 equals 1. We subtract 2 plus root 3 from both sides. So let's go ahead and subtract 2 plus root 3 over 4 minus 2 plus root 3 over 4 minus 2 plus root 3 over 4, using parentheses because it's important to. So that gets us sine squared pi over 12 equals 4 over 4 minus 2 plus root 3 over 4. And so this is equal to 4 minus 2 plus root 3 quantity over 4, which is equal to 2 minus root 3 over 4. That's sine squared pi over 12. So we take the square root of both sides, and we get sine pi over 12 is equal to square root of 2 minus root 3 over 2, and it's positive since the angle is in quadrant 1. Okay, the next problem is number 11, which is given sine of A equals 3/5, please ignore that, cosine of B equals negative 12/13, and A is between 0 and pi over 2, and B is between pi and 3 pi over 2. Evaluate cosine of A plus B. So that's all the information we have to start off. A is in quadrant 1, so there's A, and B is an angle in quadrant 3, since it's more than pi and less than 3 pi over 2, so this is B. And sine of A is 3/5, and cosine of B is negative 12/13. So cosine of A plus B, if we remember our trig identities, is equal to cosine of A, cosine of B, minus sine of A, sine of B. And to find, we know some of these. We know sine of A and cosine of B. So now we just have to figure out what cosine of A and sine of B are and evaluate, plug those all in and simplify. So we'll go ahead and do that first. We'll find what cosine of A is. So we know that sine A squared plus sine squared A plus cosine squared A is equal to 1. And we know this is equal to 3/5 squared plus cosine squared A equals 1. So 9 over 25 plus cosine squared A equals 1. So that tells us cosine squared A is equal to 25 minus 9, which is 16/25. Finally, cosine of A is plus or minus the square root of 16 over 25. Whoops. Which is equal to plus or minus 4 over 5. And since A is in quadrant 1, we're positive, positive. So cosine A is positive 4/5, 4 over 5. Okay. So now we know cosine of A. So I'm going to go back to the top and write that down with it. Cosine of A is 4/5. Now we'll find sine of B. Okay, let's do that up here. So if I remember, b is in quadrant 3, so it's going to be negative, negative. So the sine of b is negative. We know sine squared b plus cosine squared b equals 1. Sine squared b plus negative 12/13 squared equals 1. That's 144 over 169 equals 1. Sine squared b. And so that tells me sine squared b equals 169 minus 144, which is, I think, 25. Yeah, 25 over 169. So then that sine b is the plus or minus the square root of 25. 25 over 169. So it's plus or minus 5/13. And as I said before, b is in quadrant 3, so it's negative, and so we take the negative square root. So this equals negative 5/13. So sine is negative in quadrant 3. So let's go back and put that in next to cosine of b. Oh, there we go. So that tells us, now we know sine of b is negative 5/13. So now we know sine A, cosine B, sine B, and we can use all those to find cosine of A plus B. So this is equal to cosine of A, which is 4/5, cosine of B, which is equal to negative 12/13, minus sine of A, which is 3/5, 3/5, sine of b, which is negative 5/13. And we'll evaluate all this. So we get negative 48 plus 15 over 160, 15 times 5 times 13, which is 65. And negative 48 plus 15 is negative 33 over 65. Super. So that would be the result. Okay, so next question is about 18 from Unit 5, and this is solve the equation 2 cosine x plus sine of 2x equals 0. And this is tricky because they don't have the same argument. One's x, the other's 2x. So what I'm going to do is use the double angle identity for sine to get them to have the same argument. So the double angle identity for sine says sine 2x equals 2 sine x cosine x. So if we make that substitution, that gives us 2 cosine x plus 2 sine x cosine x equals 0. And this helps us because now we've got everything has the same argument. We can factor things out because we've got cosine x in two places. So we would factor a 2 cosine x out. We get 2 cosine x times 1 plus sine x equals 0. So to see what I did, you could just redistribute the 2 cosine x back through, and you would get what you started with. You're just pulling that factor out, common factor. We can divide both sides by 2. 0 divided by 2 is 0. Still 0. And so now we have, when is cosine x equal to 0? And when is 1 plus sine x equal to 0? So those are the two equations that we need to solve. And that will give us all the values of x that make this equation true. So the first one is at the top of the unit circle and the bottom of the unit circle. So this is x equals pi over 2 plus any multiple of pi. And this one is strictly at the top of the unit circle. So that would be x equals pi over 2. Oh, whoops, sorry. 1 plus sine x equals 0, so that means sine x equals negative 1. Not the top, but the bottom of the unit circle. it actually ends up not mattering. This is x equals 3 pi over 2 plus multiple of pi, multiple of 2 pi. 2 pi n. And so if we look at this, this one is actually shown over here. That's one of our answers from the cosine x part. So it's really just this set of numbers: pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2. So all the odd multiples of pi over 2 would make that equation true. And to verify it, you can just plug these in, and you should get 0 as a result. Okay. Okay, question 20 says that you are practicing for your next flute performance, and you set a tone generator to play F sharp, which is, F sharp is about 370 hertz. 370 hertz. And you play your F sharp on your flute here at beat frequency of 4 beats per second. So your frequency is close to F sharp, but not exactly, and you hear a frequency of 4 beats per second. So what two frequencies could you be playing on your flute? So your F minus 370 has to equal 4, because the beat frequency is just difference in frequencies. So if your frequencies are really close together, if they're just one hertz apart, you have a beat frequency of 1 time a second, so it's slow. If your frequencies are further apart, then your beat frequency picks up and you have more beats in a second. So 4 beats in a second means that our frequencies are within 4 from each other. So your frequency is, what this is saying is that F minus 370 is equal to 4, or F minus 370 is equal to negative 4. So you're either 4 higher or 4 lower than it. So F is equal to 374, or F is equal to, your frequency is equal to 366. So those are the two frequencies you could be playing because to have this beat of 4 per second. Okay, the last problem is number 22, which is we've got a function of theta, which is a single cosine, 8 cosine of theta minus 300 degrees. And we're trying to write this as a linear combination. And remember, a linear combination is of the form A cosine theta plus B sine theta. Or A cosine x plus B sine x. So we've got the one cosine, we're trying to get it into this form. So to go from the single cosine to the linear combination is actually not too bad. You just have to apply the cosine of an angle difference identity. Cosine of an angle difference. Remember, cosine of A minus B is equal to cosine of A cosine of B plus sine of A sine of B. And we've got theta and 300 as our A and B. So this is A and this is B. Okay, so we're going to just apply this identity, and that tells us that we have 8 times cosine of theta cosine of 300 degrees. That 8 is multiplying everything, so plus sine of theta sine of 300 degrees. Okay, and now we just think about what's cosine of 300, what's sine of 300. Cosine of 300, if you were to go to the unit circle, 300 degrees, so this is 270, so that would be 300. And the cosine is equal to half, and the sine is equal to negative root 3 over 2. So that point right here is 1/2 negative square root 3 over 2. And so that tells us now we have 8 times 1/2 cosine theta plus square root 3, minus, because it's negative square root 3, give me an eraser, negative square root 3 over 2, sorry, minus square root 3 over 2 sine theta. multiply everything by 8, and that gets us 4 cosine theta minus 4 root 3 sine theta. And there's our linear combination of cosine and sine. And to double check that this is true, what you could do is graph the original function in degrees, graph this one in degrees, and they should match up. They should be the same function. Okay, so that's going from the single cosine to the linear combination. Whew! All right, that's all the problems that you guys have asked for. And so I'm going to put this up on YouTube, and in the bottom will be links to each individual problem at timestamps. So hopefully this will be helpful in your studying.